Hi, everyone. My name is Pranathi Bingi, and I'm a senior microbiology major with minors in chemistry and psychology. I conduct research at the Ramba Lab in the TTU-HSC Department of Surgery. And today, I'm excited to be presenting to you my thesis, which is entitled Evaluating Bacterial Genotypic and Phenotypic Changes after Repeated Glycoside Hydrolysis Treatments. To begin my discussion, I will be talking about chronic wounds. Chronic wounds are a critical healthcare concern and result in significant economic burden. Within the United States alone, around 6 million people are treated for chronic wounds annually. And just one type of chronic wound, venous ulcers, costs around $3 billion to treat annually. Chronic wounds are the result of improper healing. This healing is often obstructed by bacterial biofilm infections. Biofilms are bacteria that are grown with a protective layer known as the extracellular polymeric substance, or EPS. This EPS is composed of various things, including exopolysaccharides, which are sugar-like molecules. This EPS is of particular significance because it provides the bacteria within the biofilm with various benefits, including antibiotic tolerance. However, antibiotics are one of the major treatment options available for chronic wounds and bacterial biofilm infections. This is where biofilm dispersal comes in. Biofilm dispersal involves breaking up the EPS as a potential therapy for combating these infections and increasing antibiotic efficacy. Glycoside hydrolases, or GHs, are an enzyme that targets the exopolysaccharides within the EPS of these biofilms. Exopolysaccharides act as a scaffolding within the biofilm EPS, and therefore by targeting these exopolysaccharides, we are able to break down the biofilm and disperse the cells within the biofilm. Previous work in our lab has shown that GHs are able to effectively disperse biofilms composed of Pseudomonas aeruginosa and Staphylococcus aureus, which are strains of bacteria commonly found in chronic wounds. However, clinically, GHs would need to be utilized in multiple and repeated treatments. And it is not determined if bacteria are able to mount genotypic or phenotypic changes in response to repeated glycoside hydrolase treatment. For instance, if bacteria are able to mount resistance to GHs after repeated treatments, GHs will not be able to be an effective treatment over an extended period of time. For instance, in MRSA, or methicillin-resistant Staphylococcus aureus, methicillin is an antibiotic that cannot be effectively used to treat that specific strain of Staphylococcus aureus. That leads me to my hypothesis. Because GHs are not bactericidal in nature and instead target the scaffolding of the bacteria, we predicted that bacteria will not mount resistance to GHs after repeated treatment. In order to test this, I used an in vitro biofilm model. In this model, I grew biofilms in a polystyrene well plate and treated these well plates biofilms with GHs over repeated passages. Interestingly, I found that the bacteria within these biofilms lost their ability to form biofilms, therefore making my original hypothesis impossible to test. However, this raised interesting questions about the ability of bacteria to adapt their biofilm forming capabilities in response to different environments. This leads me to future experiments in which I hope to use antibiotics in order to create pressure and see if bacteria change their biofilm forming abilities. I'm excited to be able to conduct future experiments such as this and many others in the upcoming year as I pursue my STEM MBA at the Rawls College of Business at TTU. Before I conclude my presentation, I would like to thank the Honors College for providing me with the opportunity to write a thesis. I would like to thank my PI and thesis director, Dr. Rumba, once again, and I would like to thank Dr. Lakeman, my second reader. Finally, I would like to thank Dr. Whitney Redman for her endless amount of help on my thesis and with research within the lab. Thank you so much, and Rechem.